Alright, welcome to the second video for area of regular polygons. We are going to go through some examples here. You'll want to keep the formula from part 1 in mind. You'll want to keep, if the formula doesn't really make sense to you, you'll want to keep in mind the idea that we can form these different triangles, and we can always use that to help us out as well. So, make sure you have a calculator ready to go, because there will be Pythagorean theorems sometimes, there will be trigonometry sometimes. So you're going to want your calculator ready to go. Alright, example 1. Find the area of the regular octagon with an apothem of 8 centimeters and a radius of 12 centimeters, round to the nearest tenth. Okay, so they tell us that the radius is 12 centimeters, which is not drawn into the picture for you, so let's add that. You'll notice that they give us half of one of those bigger triangles that we can form here. And since this is an octagon, we know that in the end there are going to be 8 of those triangles. So we could either use the formula, or we could find the area of one of those triangles and multiply that answer that we get by 8 to get the whole area. Now either way, we know that the height of the triangle is 8, but we don't know what the base is yet. So this is where we're going to need to do something. Now, if we just look at the original triangle that they gave us, we know that we have 12 as the hypotenuse, 8 is one of the legs, and we're missing this part, which is half of that base length. But we can use Pythagorean theorem to figure it out. We know that 12 squared equals 8 squared plus x squared. 12 squared is 144, and 8 squared is 64 plus x squared. We'll subtract 64 from both sides to get x squared by itself. 144 minus 64 is 80, and that equals x squared. To get x by itself, we will square root both sides. And when we type in square root of 80, we get approximately 8.94. Now remember, that's going to be half of the length of that base segment. So we'll want to double that. And then we find out that this whole segment down here, one of the sides of the octagon, is about 17.89. I just went straight from the calculator, so I didn't get 0.88. It's going to be that many centimeters. So now, we know that in this triangle that the height of it is 8, and the base is 17.89 approximately. So the area of one of the triangles is 1/2 times 8 times 17.89. So if we type that in, 1/2 of 8 is 4, so we would have 4 times 17.89, and that gives us 71.55 centimeters squared. But that's only the area of one of the triangles. If we want the area of all of the triangles, we're going to need to take that answer, and there are 8 triangles that we could fit in here, so we'll take that and multiply by 8. And that gives us that the area of this particular octagon is 572.4 centimeters squared. Notice I only went to 0.4 because we were told to round to the nearest tenth. I'm just trying to follow those directions as closely as I can. Also notice the units. All part of making this make more sense, especially if we see real-life applications of these, where we'll, having centimeters squared is going to be a huge difference from having miles squared. So units can be important sometimes. So that's how you would do that one. We didn't really use the formula, but if you think about the steps that we took, we kind of did. If I had multiplied by 8 here at this step, when we were finding the triangle, that would have basically meant that I was taking the side length of 1 and multiplying by 8, which would then give me the perimeter. So it's just 2 different ways to look at the same idea. All right. So, next, we have the area of this regular hexagon to find. So what I would always invite you to do is, draw in that whole triangle. Since this is a regular hexagon and that's a radius, we know this is going to have a length of 4 as well. What I want to do now is I want to sort of take this triangle and I want to make it bigger, just so that we have more room to see what's happening. That's 4, that's 4. What I want you to notice is we can figure out, and we're going to need to in this problem because we need the apothem length and we also need the base length, and we don't have either of those yet. But what I want you to notice is that we can come up with what, let me erase the apothem for now, redraw parts of the triangle again. We'll come back to the apothem soon. But we can figure out how big this angle is here. Because remember, when we make, and we're going to be able to make 6 triangles, they're all going to have the same angle there. And all we have to do to find it is do 360 divided by the number of sides here, which is 6. And 360 divided by 6 is 60 degrees. When I draw the apothem in, I'm splitting that 60 degrees in half. So this angle right here is 30 degrees. And this little angle here is also 30 degrees. So let's say that we wanted to find the length from here to here. We wanted to find that. We know this is a right angle. This is where trig is going to come back in a little bit. So if you look, let me switch to a different color for this. For this triangle, this 4 is the hypotenuse. And for this 30-degree angle that's here, we know that x is the opposite, or the, opposite side. I don't know why I wrote A. So we have O and H. Thinking back, we have so, ka, toa. So, S-O-H. So we're going to use sine here. And what we can set up is that sine of 30 degrees equals the opposite side, which is x, over the hypotenuse, which is 4. So if we want to find out what x is, what we're going to do is we'll multiply both sides by 4 to get rid of the 4 over here. And we need 4 times sine of 30. And if you do 4 times sine of 30 correctly in your calculator, what you'll discover is that x equals 2. So we know that this has a length of 2, which means that this from here to here will also have a length of 2, which means that the bottom is altogether a length of 4. And that's part of what we need in order to be able to find the area. But now that we know that this length is 2 and this length is 4, we can use Pythagorean theorem to find this missing length. So 4 squared equals 2 squared plus x squared. 4 is the hypotenuse still. Tells us that 16 equals 4 plus x squared. So we'll subtract 4 and subtract 4. We'll get that 12 equals x squared. So if we take the square root of 12, we discover that now the missing leg, which is the apothem, has a length of about 3.46. So we have a lot of information now. We know the apothem. That's all the work in blue. We know that the base of the triangle altogether has a length of 4. And so now the rest of our work is actually going to be really, really easy compared to what we just did. The area of one of the triangles is going to be 1/2 times that base length, which altogether is 4, times the apothem, which is 3.46. If we type that in to our calculators, what we end up discovering is that we have an area for one of them of 6.92. But how many triangles are there altogether? That's the area of this whole thing, but how many of these are there? We know that there are 6. So if we want the area of the hexagon altogether, we're just going to take what we just got and multiply by 6. So you should find that it has about an area of 41.52. I'll throw the units squared on here because it's a good habit to get into. That is a lengthy process. There's a lot of work that goes into it. It is a big problem. But there's nothing new in this problem that you have not seen before. It's putting many things that you've learned throughout the year together into one problem. This next one has something about it that makes it a little bit easier, in that this time you're given the base of the triangle. Now this is a 5-sided shape, but when you're setting up the area of the triangle equation, you already know that's going to be 1/2 of 20 times whatever the height is going to be, and that's something we still have to discover. So we'll do a similar setup to last time. We just need to know this time what that is. So let me draw it bigger like I did last time. This is 20. If we want to figure out this angle up here, we're going to do 360 divided by 5, since there are 5 sides to the shape altogether. 360 divided by 5 is 72. So when I drop the apothem down, half of that is going to be 36. 72 divided by 2 is 36. And when I drop the apothem down, this 20 splits temporarily into 10 and 10. I want to know the apothem. So what I'm going to set up then is another trig problem. We know the angle here is 36. Here's our apothem. Here's the opposite side over here. The apothem is not the hypotenuse. The hypotenuse is this radius over here, this one. We're not dealing with that. So we have the adjacent side and we have the opposite side. So ka toa, T-O-A, tangent is what we're going to use here. So tangent of 36 equals 10 over x, opposite over adjacent. What I'm going to do is I'm going to turn tangent of 36 into a fraction by putting it over 1 and then cross multiply. 1 times 10 is 10, and that's going to equal tangent of 36 times x. To get x by itself, I'm going to divide by tangent of 36. But I have to do it on both sides. So 10 divided by the tangent of 36 gives us 13.76 approximately as the apothem. So now we can finish up our area equation for our triangle. We know it's going to be 1/2 times 20 times 13.76. Looks like I just moved the problem a little bit, but that shouldn't matter at this point. Sorry about that. So if we type in 0.5 times 20 times 13.76, that's giving us 137.6 as the area of one triangle. So to get the area of the pentagon, what you're going to do is you're going to take that number, multiply by 5, giving you about 688. In this case, we have units squared. I think you've seen enough examples at this point. All the problems are going to have variations on this idea where you have to use a little bit of trig or Pythagorean theorem sometimes, to figure out the area. I really like the triangle approach because I think it makes more sense than anything else. I think it connects back to things that you have seen before, which makes it easier to handle. So, you are now ready to try out the problems. Good luck with those, and I will see you in the next video.